All right, guys, this is it. We are finally learning actual stoichiometry. So this is a lesson 11.3, and we're starting off with something called mole-to-mole stoichiometry. So we're going to learn how, we're going to understand how to solve mole-to-mole stoichiometry problems. We're going to learn how to set those up using something called mole ratios, and we're going to be able to solve those mole-mole stoichiometry problems. So let's start off with a definition of stoichiometry. It's kind of a scary sounding word. But basically what stoichiometry means is it's a quantitative relationship between the amounts of substances in a chemical process. And it relies on the law of conservation of matter, which means it requires a balanced chemical equation. So you guessed it, we're going to have to be balancing some equations in these problems. All the problems that we do in stoichiometry have to start with a balanced chemical equation. If you don't have a balanced equation, you cannot do a stoichiometry problem. And once you have that balanced equation, stoichiometry uses conversion factors, such as some that we've already seen. Last lesson, we learned about molar mass. This lesson, we're going to be learning about mole ratios. We might also, in stoichiometry problems, have to use density or concentration. But basically, all those conversion factors are going to convert the amount of one substance in a reaction to the amount of another substance in a reaction. So let's take a look at this reaction down here. We're starting off with CH4, we're adding some O2, and we're forming CO2 and H2O. But look at those quantities. We have one CH4, two O2s, and that forms one CO2 and two H2Os. And we can see that also by looking at the coefficients in our balanced chemical equation. Because this equation is balanced, it's satisfying the law of conservation of matter. Those ratios always stay the same. And that is the foundation of all stoichiometry problems, the ratio between the different reactants and products, and those are called mole ratios. So let's talk more about mole ratios. Mole ratio, by definition, is a ratio of elements or compounds in a balanced chemical equation using the coefficients from the balanced chemical equation. And a mole ratio essentially is a type of conversion factor that we're using to convert from one type of moles in the reaction to another type of moles, one substance to another substance. All stoichiometry problems use a mole ratio. Using the mole ratio is what makes it a stoichiometry problem, because that's what's going to allow us to switch between different substances in a chemical reaction. So the first thing that we need to be able to do is we need to be able to set up our mole ratios, these conversion factors that we're going to be using. So looking at this chemical equation, let's look at our coefficients. We've got a coefficient of 2 in front of our hydrogen. There's nothing in front of oxygen, which remember means that it's a 1. And then we've got a 2 in front of our H2O. So if we want the ratio of hydrogen to water, we're going to set it up like a fraction. And it's a mole ratio, so our unit is moles. So we have 2 moles of hydrogen, and hydrogen is H2. I'm getting that 2 from the coefficient. There's 2 moles of hydrogen for every, 2 moles of water, H2O. And that 2 moles of water comes from the coefficient in front of water. So that right there, that is a mole ratio. In this chemical equation, there are 2 moles of hydrogen for every 2 moles of H2O. That's our mole ratio. Take a moment and see if you can set up the mole ratio of hydrogen to oxygen, just as I've done in this problem. We're looking for hydrogen to oxygen. All right, so hydrogen to oxygen, you should have come up with 2 moles of H2 per 1 mole of O2. That would be our mole ratio. 2 moles of H2 per 1 mole of O2. And then finally, let's set up one more just to make sure we have the hang of this. Let's set up our mole ratio of oxygen to water. Take a moment and see if you can write your mole ratio of oxygen to water, exactly as I have. Make sure that you include the units mole and the substance, and then it should set up like a fraction, like I've set it up here. And your answer should look like this: 1 mole of O2 per every 2 moles of H2O. So these are 3 examples of mole ratios that we've set up for this problem. And we could set them up in the other direction. We could flip any of these mole ratios. For example, if we wanted the mole ratio of water to hydrogen, if we wanted to flip that, it would be 2 moles of water per 2 moles of H2O. This would just be flipped. So as long as we're using those coefficients from that balanced chemical equation, we can set up any mole ratio we want to compare our reactants to our products or the reactants to each other. So that's how you set up a mole ratio. On the next slide, we're going to take a look at how we can use mole ratios to do a stoichiometry problem. So for stoichiometry, we're going to start off, as I mentioned, with mole-to-mole stoichiometry. Mole-to-mole stoichiometry is anywhere that you are given moles and you're solving for moles. And we're converting between 2 different substances. So that's what makes it stoichiometry. So you'll also hear me refer to mole-to-mole stoichiometry as a one-step stoichiometry problem. In this type of problem, you're given the moles of one substance and you are solving for the moles of something else. It has to be a different substance. We have to be converting our moles from one substance to another. And a mole-to-mole stoichiometry problem only needs one conversion factor, and that is your mole ratio. So an example of what one of these problems looks like is here. How many moles of O2 are needed to react with 3.00 moles of H2? So at the beginning here, this is what we're solving for. We're solving for how many moles of O2. And we are given 3.00 moles of H2. So our given information is where we're going to start. Always start with your given information. So I'm going to write down 3.00, and then we need our unit with our substance. Always need both of those things, 3.00 moles of H2. That is our given information. So we have moles, so we're going to use our mole ratio to convert from moles of H2 into what we want, which is moles of O2. So let's set up our mole ratio. As always, in any sort of conversion problem, dimensional analysis problem, the unit that you were given goes on the bottom. So I was given moles of H2. So I'm going to write moles of H2 on the bottom. Notice how I'm not writing a number with that yet. I'm just writing the unit because I want to set up my conversion factor, and then I'm going to go back and fill in my units. The unit that I want goes on top, and I want moles of O2. So on top of this conversion factor, this mole ratio, I'm going to write moles of O2. That's what I want. And this is a mole ratio. We've got moles of what we were given on the bottom, moles of what we want on top. Classic mole ratio. So to get the numbers to fill in here next to our units, we have to look at our balanced chemical equation. This is the same equation from the other page. There's 1 mole of O2 for every 2 moles of H2. So my ratio is 1 mole of O2 per 2 moles of H2. And you can see when I set this up, my 3 moles of H2 is in the numerator and the denominator. So that unit cancels out. Not the number, leave the numbers, but we're canceling out the unit, moles of H2. And the unit we're left with is one we're solving for, moles of O2. So now I can solve this. 3 times 1 divided by 2 is 1.50 moles of O2. We need 1.50 as our answer because we need to have 3 sig figs to match the sig figs that we started with. So that's a mole-to-mole stoichiometry problem. Again, just a quick recap. We started off our given information 3 moles of H2. So I put that as my given information. We were solving for moles of O2. So the unit I started with, I put on the bottom of my conversion factor, and the unit I want, I put on the top of my conversion factor. And that's a mole ratio, moles of O2 per moles of H2. The numbers for your mole ratio come from your coefficients. So there's 2 H2s, there's 1 O2. So I filled that in. And then we just solve. 3 times 1, all of that divided by 2, and 3 divided by 2 is 1.50. So we need 1.50 moles of O2 to react with all 3 moles of our H2. And that would be the final answer to this problem. And here's that answer again for you. Same thing, just typed out because I know my handwriting's a bit messy. It's also color-coded so you can see where my given information is and where my answer is. So that's going to be the same setup for all of your mole ratio problems. So I want you guys to now try the rest of those problems in 11.3. Again, we'll go over them during class, but make sure that you set up those problems. Always put your given information as the first thing you have. Your mole ratio goes in the middle, what you want on top, what you've got on the bottom. The numbers come from the coefficients in your balanced chemical equation. And then solve it for your final answer. Make sure you include the units of what you're solving for. So go ahead and try the rest of the problems in 11.3. We'll go over them in class next time I see you. And have fun, everybody.